In this section, we will talk about the derivatives of logarithms and some applications. Here's an example. F of x equals to 9x plus 3 times e to the negative 5x. It has one critical number. We need to find the critical number. So recall that critical numbers occur when either f prime of x is equal to 0 or f prime of x is undefined. Okay, this is when critical numbers occur. So we want to find the critical number. But this is a product of two terms. So we got our first term, which is a, and our second term, which is b. And the product rule says that the derivative of a product is a prime b plus b prime a. So first let's find out what a prime is. A prime is the derivative of 9x plus 3. So a prime is simply 9. So that's a prime times b, which is e to the negative 5x. Then we got plus b prime a. B prime, so recall that if you have e to the u power, where u is anything other than x, then the derivative of that is going to be e to the u times u prime. Okay, that is the derivative of e to the u. So u is negative 5x. So because this is not a complicated function, we can just plug it into this formula. So e to the u is e to the negative 5x times u, or times u prime, which is going to be negative 5. So we're going to multiply this by negative 5. So that's just going to be b prime. B prime is going to be this thing, the derivative of e to the negative 5x, which is e to the negative 5x times negative 5. But we also have to multiply that times a. So we're going to multiply this by 9x plus 3. Okay, then I'm going to simplify this a little bit. So this equals to 9e to the negative 5x plus, I can distribute this negative 5. So negative 5 times 9 is negative 45x. Negative 5 times 3 is negative 15. So I have negative 45x minus 15. And that is times e to the negative 5x. So that's f prime of x. Now, first off, where do we have critical numbers? Critical numbers is when the first derivative, or f prime of x, is equal to 0 or it's undefined. So one thing we have to remember is that e to the x is always greater than 0, which means e to the x cannot equal to 0. It's only strictly greater than 0, cannot equal to 0. So even though this goes to the denominator, e to any number cannot equal to 0, so we don't have a case where f of x is undefined. Okay, that's not going to happen. So let's figure out when f prime of x is equal to 0. So I set this whole thing equal to 0. And they both have a common factor of e to the negative 5x. So if you think back to algebra, when we solve an expression or an equation that has two like terms, we need to factor that out. So if I factor out e to the negative 5x, here's what's left over. If I take out the e to the negative 5x, I'm left with a 9. And if I take out the e to the negative 5x, I'm left with a negative 45x minus 15. Okay, I'm going to simplify this. So I have e to the negative 5x. 9 minus 15 is negative 6. So I have negative 6 minus 45x. By the zero product property, if two factors multiply to be 0, then either e to the negative 5x has to equal to 0, or negative 6 minus 45x has to equal to 0. Now, e to any number can't equal to 0 because e to the x is strictly greater than 0. So this cannot happen. So if we solve this one, we add 6 to both sides. We get negative 45x is equal to 6 divided by negative 45. So if you simplify this, x is equal to 6 over negative 45. You divide these both by 3, and this gives you negative 2 over 15. So the critical number is negative 2 over 15. Now remember, the critical number is where the graph is going to hit a maximum or a minimum. So the critical number is when the graph hits a maximum, where the slope is 0. This is why we set f prime of x equal to 0, or where it hits a minimum. So if we want to check our answer, we would go to Desmos and we would graph the original function. If we did it correctly, the function is going to have a maximum or a minimum at x equals to negative 2 over 15. Okay, so let's go ahead and plug in the original function into Desmos real quick. Okay, so I go to desmos.com. My original function is f of x equals to 9x plus 3 times e raised to the negative 5x. And there we go. Our maximum is going to be at this point where the x is negative 0.133. And if you take negative 2 divided by 15, it's negative 0.133. So we did it correctly, and we have a critical point, which is the maximum over here, and that's also where the slope of the tangent line is equal to 0. Okay, next example. Given the function f of x equals to 5x plus 3 minus 6x, we need to find the equation of the tangent line at the point 0, negative 3. Now, first of all, the equation of any line is going to be in the form of y equals to mx plus b. And f prime of x is the slope, which is the m of the tangent line. So first thing we have to do is we got to find out what is f prime, that gives the slope of the tangent line, and then we got to find f prime at x equals to 0. So f prime of x, derivative of 5x is going to be 5. Derivative of 3 is going to be 0, so I'm not going to even write that. And remember that the derivative of e to the x is just equal to e to the x. So this gives me minus 6 e to the x. Okay, that's our derivative. Now, we want the slope of the tangent line, which is the first derivative, at the point x equals to 0. So we want to figure out what is the slope of the tangent line, f prime, at the point x equals to 0. So this is 5 minus 6e to the 0 power. This is equal to, so f prime of 0. Once again, f prime is the slope of the tangent line at the point x equals to 0. E to the 0 is 1, so we got 5 minus 6, which is negative 1. That's just the slope of the tangent line. But we had to find the equation of the tangent line, which is in the form of y equals to mx plus b. So we know that y is negative 3. We know our slope m is negative 1. X is 0, and we got plus b. So 1 times 0 is 0, which means we get b is equal to negative 3. So the equation of the tangent line is y equals to our slope, which is negative 1 times x, plus b, which is negative 3. And once again, we could and we should check our answer using Desmos. So let me show that real quick. So we got to graph two things here. First, we have to graph the original function. The original function is this. It's f of x equals to 5x plus 3 minus 6e to the x. And the slope of the tangent line we said is y equals to negative x minus 3. See, at that point, 0, negative 3, the slope of the tangent line is negative x minus 3. So it's going to hit that graph at the point 0, negative 3. So this looks correct. And once again, on exams, you should always be checking your work. Okay, next example. We have another formula. When you have the derivative d dx of log base a of x, it's equal to 1 over ln a times 1 over x. Just a formula we have to know. So we have f of t equals to 550 plus 403 times log base 7 of t. Determine f prime of 3. So first of all, we got to find out what is f prime of t. We got to find the general form of the derivative. Derivative of 550 is 0, so I'm not going to write that. Then I have 403. Now, the formula says that if you have log base a of x equals to 1 over ln a times 1 over x. So that's going to be 1 over natural log of the base, which is 7, times 1 over x, which in this case is going to be t. And now we want to find out what is f prime of 3. So the t-value is equal to 3. So we have 403 times 1 over the natural log of 7 times 1 over 3. And you just put this all into Desmos, and you're going to get 69.0337. Next example. I changed this to P because it makes more sense. I don't know why there's D in the original problem. I changed it to my open math also, but it says the demand for cat food is given by P of x equals to 70 e to the negative 0.06x, where x is the number of units of cat food sold. So remember, x is the number of units, and P of x is the price in dollars. So first we want to find the revenue function. Here's what we know. The revenue is the price times the quantity sold. So P of x is 70 e to the negative 0.06x times x. So this is our revenue function. Okay, revenue is price times quantity. Find the number of units that will maximize the revenue. So the revenue gets maximized when r prime of x is equal to 0. Or is undefined, but that's not going to happen, so we're going to maximize revenue when the first derivative is equal to 0. So let's find the first derivative. To find the first derivative, we have to use the product rule. Okay, let me rewrite the function over here. We got r of x equals to 70 e to the negative 0.06x times x. So this is our a, and this is our b. So we know the derivative is a prime b plus b prime a when we have a product rule. So let's take the derivative of a. Okay, the formula says that if you have e to the u and we take the derivative of that, that's going to be e to the u times u prime. So 70 is a constant, stays where it's at. E to the u is going to be e to the negative 0.06x, and we have to multiply that by the derivative of this, which is going to be negative 0.06. All of that is just going to be our a prime, and we have to multiply that by b, which is x. Plus, we got b prime. The derivative of x is just going to be 1, so b prime is going to be 1, and we're going to multiply that by a, which is 70 e to the negative 0.06x. Let's simplify this. If I multiply 70 times negative 0.06, it is going to give me negative 4.2. So I'm going to get negative 4.2 e to the negative 4.2x. There's an x there. So 70 times negative 0.06, negative 4.2, there's still an x. So I have negative 4.2 times x. And then I still have the e to the negative 0.06x. Plus 1 times all of that is going to be 70 e to the negative 0.06x. Okay, now this has a common factor of e to the negative 0.06, so we can factor that out. And we're left with negative 4.2x plus 70. Now the thing is that to find the maximum revenue, we have to set the derivative equal to 0. And by the zero product property, either this has to be 0 or this has to be 0. So let me do that over here. Either e to the negative 0.06x has to be 0, which can't happen because e to the negative point anything, e to anything is always going to be greater than 0. It can't ever equal to 0. That's not going to work. Or negative 4.2x plus 70 is equal to 0. So for that, we subtract 70 divided by 4.2, and we're going to get x equals to 16.67, which we're going to round up to be 17 units, because we can't sell 16.67 units. So 17 units is what's going to maximize the revenue. Now we got to find the price. So the price is going to be this function. P of x, our price function, is 70 e to the negative 0.06x, where x is the quantity sold. So the price when 17 units are sold is equal to 70 times e to the negative 0.06 times 17. You can just put all of this into like Desmos or a calculator, and we're going to get that the price that's going to maximize revenue is $25.24. Okay, and last example we'll do in class.